Hi everyone, in today's video we'll talk about Swin Transformer. We'll look into the GitHub repository and we'll try to link the pieces of code with concepts from the paper. So let's jump right in. So this is the paper. It came out in 2021. It's called Swin Transformer, a hierarchical vision transformer using shifted windows. So the name Swin came from shifted windows. So they have a nice figure here. Figure number 1. So these are the black squares are the patches and the red squares are the windows. So compared to VIT, VIT has the same size of the patch for all the layers. But what they are suggesting in this paper is just to group the small patches into windows, and in addition to that, that window will be shifted alternatively inside the Swin Transformer layers. So they are proposing a hierarchical vision transformer, and the hierarchical concept is not new in image classification. If you go to this paper, the new cognitron, a self-organizing neural network model for a mechanism of pattern recognition unaffected by shift in position, by Kunihito Fukushima. This paper came out in 1980. And if we jump into this paragraph, according to the hierarchy model by Hubel and Wiesel, the neural network in the visual cortex has a hierarchy structure, LGB, lateral geniculate body. I'm not familiar with these terms. So simple cells, complex cells, lower order hypercomplex cells, higher order hypercomplex cells. It's also suggested that the neural network between lower order hypercomplex cells and higher order hypercomplex cells has a structure similar to the network between simple cells and complex cells. In this hierarchy, a cell in higher stage generally has a tendency to respond selectively to a more complicated feature of the stimulus pattern, and at the same time has a larger receptive field and is more insensitive to the shift in position of a stimulus pattern. So this is why you can find the hierarchy structure in almost any image classification method, like convolutional neural network and a Swin Transformer and the new cognitron. So this is why the higher stage cells, which in this case the larger windows, can respond selectively to more complicated features. So because they can look into multiple windows, multiple smaller windows, they can respond to more selective features. So they so let's say just like in convolutional neural networks, where the neurons in the first layers can respond to edges, sharp edges, the orientation of edges, and the neural in the lateral layers they can respond to curves and more complex features. Also, there is a good figure here. So this shows the hierarchical structure for the new cognitron. But why the new cognitron did not take off? The reason for that is explained in this paper, deep learning paper, which came out, I think, in 2015. I think that it came out in 2015. Yes, 2015 here. And by the way, this is a go-to reference for anything about deep learning. It summarizes decades of research, and it's written by the pioneers in deep learning field. So it's basically, it's more like a white paper more than a research paper. So it summarizes all of that. So here they discuss the convolutional neural networks. Yeah, here. ConvNets have their roots in the new cognitron, the architecture of which was somewhat similar, but did not have an end-to-end supervised learning algorithm, such as backpropagation. So that's what was wrong with the new cognitron. It proposes extracting the features in a very good way, but it doesn't have end-to-end supervised learning. So it didn't have backpropagation. So the hierarchical structure, which was used before, was the motivation behind the Swin Transformer, because it was missing in the original VIT. Original VIT did not have the growing windows or shifting windows. They only have patches, and you set the size of the patch at the very beginning as a hyperparameter. So today we're going to look into the code in the Swin Transformer GitHub repository. We're interested in the code of the first Swin Transformer. This is the paper that we're interested in. I basically borrowed the classes and functions from these three files: the Swin Transformer, build, and make file. I collected all of these into a notebook, Swin Transformer annotated. By the way, you can find all the notebooks that I'm working on in the description below on my GitHub. Just to have an idea about Swin Transformer, let's look at the architecture. This architecture here. So we're dealing with, it can come in different architectures. They basically discussed different architectures here. Swin T, I think it stands for Swin Tiny, Swin Small, Swin Big, and Swin Large. So we're testing this architecture here, which comes with the 4 layers, each of which has 2 Swin blocks. And the first layer has 2 Swin blocks, the second layer has 2 Swin blocks, the third layer has 6 Swin blocks, and the final layer has 2 Swin blocks. The Swin blocks, we're going to discuss the Swin blocks later, but generally it is this architecture here which comes inside each one of the layers. But just look at how the tensor, the multidimensional array, we feed a multidimensional array to the Swin Transformer. We'll see how does it change in shape until we get into the final classes, the final image classes. So this is the code I'm working on. By the way, you can find all the notebooks that I'm showing in this video in the description below on my GitHub. I borrowed some code from the Swin Transformer GitHub repository, and this is the piptech entry for the paper. I'm installing some dependencies and importing the libraries. Here, the start of the Swin Transformer classes and helper functions, which I get from these 3 files: the class MLP, window partition, window reverse, window attention, Swin Transformer block, patch merging, basic layer, patch embedding, and the class Swin Transformer, which packages everything into one model. So I initialize the model with the default parameters. You can find the default parameters in config file in the Swin Transformer. But these are the default parameters. I think I kept everything the same. I changed the image size to 32 because I'm using C14 dataset. The number of classes is 10. The window size, I changed it to 4. And I think I kept everything else same. Yeah. So this is the model. I'm initializing the model, and I'm downloading C14 dataset using torchvision. And I'm running a single patch through the Swin Transformer just to see how the multi-dimensional array will change. So starting with a batch of size 128, we have 128 images. Each image is 32 by 32 by 3. 3 is the RGB channels. So the patch size, we set it to 2 by 2, 2 pixels by 2 pixels. The first thing that Swin Transformer does, you can see it here in the paper, the patch partition. The patch partition is done using a conv2d layer. So the end channels, 3, the embedding dimension is what I set here to 96, which is the default. I think it's the default option. Let's check. Yeah. This the default embedding dimensions is 96. I kept it the same. So the end channels is 3, the embedding dimension 96, kernel size is the batch size, which is 2, and the stride is the patch size, which is 2, because we want the patches non-overlapping patches. So in the code, let's look at where patch merging happens. Here, the first thing, split image into non-overlapping patches. It calls patch embedding. Patch embedding is basically X shape trans X and through projection, and projection is defined as the conv2D. This conv2D will output 128 images, 96 channels, 16 width, 16 height. Because 32 divided by 2 is 16. So 16 along the height of the image and 16 along the width of the image. We flatten 2. If we flatten 2, here flattening, in the patch embedding, flattening in PyTorch is just flattening the dimensions. So we're giving it 2. 2 is this dimension, 0, 1, 2. And by default, flattening takes the end dimension as -1, which is the last dimension of the multidimensional array. So it will flatten these 2 dimensions. And after flattening these, we will get 256, which is 16 times 16. Then we will transpose 1 and 2. So 1 and 2 will be transposed. So we will move the channel dimension to be the last dimension. After class patch embedding, we will get a multidimensional array of size 128 images, 256 patches, and each patch has 96 channels. So the input to the first layer of the Swin Transformer, the input here will be of size 128 by 256 by 96. For the time being, just to explain the shape of the multidimensional array, we will skip what Swin Transformer block does. We will get back to that later in this video. So after layer 1 does its magic and run the Swin Transformer block, it will perform patch merging. So if you go to Swin Transformer class, you will see that it first performs patch embedding, then it calls basic layer. Basic layer has a downsample parameter. The downsample parameter is basically calling patch merging if it's not the last layer. So patch merging is done in the first layer, the second layer, the third layer, and it's not done by the fourth layer. So patch merging does the following. It creates 4 multidimensional arrays, x0, x1, x2, x3. In x0, it takes all the images in the batch and all the channels, and it samples the even rows and even columns. So H even and W even. X1 samples odd rows and even columns. X2 samples even rows and odd columns. And X3 samples odd rows and odd columns. So for example, this is a 4x4 matrix. If we done this logic, which by the way you can find in patch merging class, here, if you done this logic, this is what will happen in this example. X0 will be 0, 2, 8, 10. 0, 2, 8, 10. And X1 will be 4, 6, 12, 14. X2 will be 1, 3, 9, 11. And X3 will be 5, 7, 13, 15. These 4-dimensional arrays will be stacked along the channel dimension. So first we'll have x0, x1, x2, and x3 stacked along the channel dimension. So what will happen? Zero will become in front of 4, and 4 will become in front of 1, and 1 will become in front of 5. So 0, 4, 1, 5 are basically the the patches inside the first window. So the patches inside one window will be merged into one patch. So first, I will take 4 multidimensional arrays, and I will stack these 4 multidimensional arrays along the channel dimension in a way that that all the patches inside one single window will have their features stacked along the channel dimension. So doing this, the channel dimension will be increased by 4. This 4 by channel dimension. Swin Transformer block won't change the size of the multidimensional array. It will be changed by the patch merging class. So by the end of the first layer, we started with 128 by 256 by 96. By the end of the first layer, we will have 128 by 64. 64 is 8 by 8. We downsample these 16 by 16, we downsample them by 2, so it's 8 by 8. And the channel dimension will be 4 times C. 4 times 96, which is 384. By mapping the 384, which is by mapping 4C to 2C, 384 to 192, we will end up with 128 images, 64 patches, and each patch has 192 channels. So I got this piece of code just to make sure that the patch merging works as I expected. So the first window is 0, 1, 4, 5. 0, 4, 1, 5 will be stacked along the channel dimension, and they will be merged together. In the second layer, we will start with a multidimensional array of size 128 images by 64 patches by 192 channels. These 64 is 8 by 8, and if we downsample them by 2, it will be 4 by 4. So we will have 16 patches. And if we stack these along the channel and along the channel dimension, we will have 192 times 4, which is 768. So we will run them through a linear layer to map 4C 4 times the channel dimension to 2 times the channel dimension. So we'll end up by this, the end of the second layer will be 128 images by 16 patches by 384 channels. The third layer will do the same. It will reduce the number of patches, and it will increase the number of channels. Fourth layer, because fourth layer does not do patch merging, by the end of the fourth layer we'll end up with 128 times 768 channels times 1. Then we will run the multidimensional array through a linear layer to map the 768 channels to 10 classes. Just a small note here about the patch merging class. Notice here that we are stacking these 4 tensors along the channel dimension, and we're performing the reduction using a linear layer. So the reduction of images or the reduction of patches is done through a linear layer. For me, this is a huge shift in thinking and computer vision research, because everything now is part of the neural network. This wasn't the case when I started my research in computer vision, because researchers before, they were trying to do everything by themselves. They could run average on the channel dimension, and they would reduce that. But that's not practical. The best practice here is to make the reduction, make the patch merging part of the neural net and make it in a layer that is optimized as part of the neural net. So the neural net will decide the weights and how the patches are made. It's not up to the researcher to set the average or max. It's up to the network, and the network works as a whole unit, as a one unit. Everything is connected to the final loss in the function. So just to have an idea about this, look at this paper from 2012. It's called Multi-Column Deep Neural Network for Image Classification. Here in the experiments, they have a figure. This figure here, images P. What does P stand for? P stands for pre-processing. So they pre-process the images before training. What pre-processing is done, it's just like reducing the image size. They mentioned some operations here in the appendix. Image adjustment increases image contrast by mapping pixel intensity to new values such that 1% of the data is saturated at low and high intensities. And they use the reference 24. Reference 24 is basically MATLAB. So they use MATLAB operations, MATLAB functions to pre-process the images before training the neural net. This was done in 2012. So MATLAB has functions like mresize, which resizes images. So it can resize image by half, just like this one. So this is the original image and this is the reduced image. Do you see what I'm trying to get here? Before it was up to the researcher to run all that kinds of processing on images. So it's up to the researcher to run all kinds of pre-processing on images, resizing the images, increasing their intensity, sharpening the images. But the common practice now in research is do not touch the dataset. Just let the neural net do its magic. So when I first look at the code, I was expecting something dividing by half, running average through the channel dimension, but I didn't find any of that. They run it through a linear layer. They let a linear layer does the reduction, and that linear layer is part of the huge neural net. It's part of the huge Swin Transformer, and it's optimized as part of the neural net. So I think this is the correct way to do it. Not to touch the images and make all the operations and images optimizable by the neural net. Before I start talking about the Swin Transformer blocks, I want to talk about the LN layer, layer norm layer. So if you look into the code, this is a Swin Transformer block, and it starts by running the multi-dimensional array through a layer norm 1, and this is norm 1, and it's a layer norm from torch. So what does the layer norm do? It's basically explained in this paper, layer normalization, which came out in 2016. Normalization is basically subtracting the mean and dividing by the standard deviation, just to let that group of data to have a zero mean and unit variance. So if you check the PyTorch layer normalization, E expected is this is the mean, and this is the standard deviation plus epsilon, just to avoid dividing by 0, and these parameters are optimized with training, just to make the normalization optimizable with the loss at the end of the network. So if you go through this paper, and there's two types, the layer normalization and batch normalization. So here, the input pattern is X, and the output vector is Y, L's hidden layer, and AL is the vector representation of the summed inputs to the neurons at that layer. So AL is the result of multiplying by the weights. And the summed inputs are computed through a linear projection with the weight matrix WL and the bottom-up inputs HL, given as follows. So the neural representation AI at the layer L is the result of multiplying the weight matrix with H, and the input to the next layer will be the vector A added to the bias, run through a function. This function could be the nonlinearity, where F is an element-wise nonlinear function, and W is the incoming weight to the ith hidden unit. BI is the scalar bias parameter. One of the challenges of deep learning is that the gradients with respect to the weights in one layer are highly dependent on the outputs of the neurons in the previous layer, especially if these outputs change in a highly correlated way. Batch normalization was proposed to reduce such undesirable covariate shift. The method normalizes the summed inputs to each hidden unit over training cases, specifically for ith summed input in the lth layer. The batch normalization method rescales the summed inputs according to their variances and the distribution of the data. A bar will be the result of subtracting mu, which is the mean, from A, and dividing by sigma. GI is a gain parameter, scaling the normalized activation before the nonlinear activation function. So this is a parameter. This is in PyTorch, G here, in PyTorch terms, it's gamma plus beta. So this is batch normalization. But the problem it's typically impractical to compute the expectations in equation 2. So exactly, since it would require forward passes through the whole training dataset with the current set of weights. Instead, mu and sigma are estimated using empirical samples from the current mini-batch. This puts constraints on the size of mini-batch, and it's hard to apply to recurrent neural networks. So this is the problem, that this formulas here are dependent on a single parameter, are dependent on a single hyperparameter, which is mini-batch. So based on how do you set your mini-batch size, these two parameters will change. This is in batch normalization. That's why layer normalization was proposed, just to remove the influence of the mini-batch size. In layer normalization, mu and sigma are computed differently. Mu will be the result of the summation over all over all AIs. AIs from 1 to H. H denotes the number of hidden units in the layer. So we are normalizing by the number of the hidden units in the layer. There is a great visualization for batch and layer normalization here. So the first dimension is the batch dimension. The second dimension is the channel dimension. And the third dimension is the height and width, suggesting that this is a input image. So batch normalization normalizes each channel independently across all the samples in the mini batch. But this is the problem. This is not fixed. N is not fixed. N is changing because you set the mini batch as you want, and depending on how large or how small you set the mini batch, these statistics, the mu and sigma, will be different. This is layer norm. For each sample, you are normalizing all channels, and this is the trick. Channels are fixed. for the whole training and testing interesting samples. So what you are getting here is more consistent than what you're getting here. Because in training, you're using mini batch, and in testing, you are feeding all instances in the data set. But if you're normalizing based on the channel dimension, the channel is the same for training and for testing. So what you're getting is more consistent than batch norm. So this is the about layer norm. I have a notebook here. So I set a random generator, and I created a 3-dimensional array. And second dimension is height multiplied by width, and the channel. This is the original array, and this is the normalized array. Notice that it's the same as mean along the last dimension, which is channel, and standard deviation along with the last dimension. And I'm subtracting the mean and dividing by the variance plus epsilon. By the way, this is I get this from Stack Overflow, this answer here. And basically this is it. This is what PyTorch is doing. These two tensors are the same. So it's the mean and variance along the channel dimension, along the last dimension. So now let's get back to the Swin Transformer blocks. In Swin Transformer blocks, here they have WMSA and SWMSA. MSA stands for multi-head self-attention. So in the even transformer blocks, we are performing window multi-head self-attention. And in the even Swin Transformer blocks, are performing shifted window multi-head self-attention. So in the code here, shift size is 0 in the even transformer blocks, and it's by 2 in the odd transformer blocks. So we are alternating between windows, multi-head self-attention, and shifted windows, multi-head self-attention. In the transformer block, here I put print statements almost everywhere, just to see how the multi-dimensional array is changing. So here at the beginning of the Swin Transformer block, if the shift size is greater than 0, it will create an attention mask, and if it's not greater than 0, the attention mask will be none. So at here in layer 0, it's unflattens this dimension into 16 by 16. Then it reordered the image not in terms of images, but in terms of windows. Each window is 4 by 4 and 96 channels. So the attention is performed not between images and not between patches. It's performed between windows. It will perform shifted windows. So how does it create the shifted window? The shifted window is created here in this part of the code. So I was literally looking at this piece of code, and I couldn't. I understand that they're creating the attention mask just to mask out some values, because they're shifting the windows, and they don't want the non-touching non-neighboring windows to perform attention with each other. But I don't know how they are doing that. I came up with my matplotlib code just to understand what's going on in here. So if the window size is 4 and the shift size is 4 divided by 2, which is 2, height is 16, width is 16, and this is that image mask. They taking 3 slices for the window size, for the window and shift size and from the shift size to none. So depending on the window size and the shift size, they assign ranks for all the windows. This rank starts from 0, and when they finish the slice, they added 1. And this is how it looks. So all of these windows are allowed to perform attention with each other because they have the same rank. But these windows cannot perform attention with each other because they have different ranks. So this is done here. They're subtracting. First, it used to be 16 by 16. They are unsqueezing unsqueezing dimension 1, and they are unsqueezing dimension 2, and they're subtracting those. So think of these as, if we have the same rank, we will have 0, which they assign in the mask to 0. If we have different rank, we won't have 0. It will be some number other than 0, and in the mask we will have -100. So the mask will have 0 if the rank of the windows agree, and -100 if the rank of the windows do not agree. So what's the point of this mask? Here, if you go to window attention class, and if you scroll down here to mask, so after performing the multiplication between the query and key, they're adding the mask. If we are windows that are not allowed to perform attention together, our attention, which is multiplication of our query and key, will be so small because we added -100. But if we are allowed to perform attention together, the 0 will be added to our attention, so nothing happened. So what this mask is doing, it's just basically, it reduces the size of the attention until it becomes very negligible, just to make the network ignores that attention between the windows, because after shifting the window to the top left corner, just like what happens here, these windows are not allowed to perform attention with these windows. So this is what they explained in Figure 4, illustration of efficient patch commutation approach for self-attention in shifted window partitioning. So this is a summary of the model. Patch embedding will perform conv2d and layer norm. Then the model will stack the layers using basic layer class. And basic layer class is basically a stack of Swin Transformer blocks. So the first layer has 2 Swin Transformer. This performs window attention. The second Swin Transformer performs shifted window attention. Then at the end of the first layer, it will perform downsampling using pytorch-geometric class. The second layer has 2 Swin Transformer blocks. Here's the first one and here's the second one. The third layer has actually 6 Swin Transformer blocks. So this is the first one, second one, third, fourth, fifth, sixth, and it performs batch merging. The final layer, which is the fourth layer, has 2 Swin Transformer blocks, but it does not have patch merging layer. At the end, it will apply layer norm, and it will run these features into a linear layer to get the 1 of 10 classes. I have this notebook, which I have so many printouts just to print the size of the multi-dimensional array. I called this notebook a Swin Transformer Annotated. I have another notebook which I just kept the classes and I run it for 200 epochs on a CFAR10 dataset. I know it's not an experiment. It's not good enough to judge the Swin Transformer performance, but I just want to test the pipeline. I want just to run an entire dataset through the pipeline for 200 epochs. Of course, I have to make some compromises. I reduces the number of embedding dimensions just to make it run on Google Colab free quota. You can use it, so if you have the computational power, you can use this notebook. It's really just for running the whole dataset. So on a CFR10 dataset, I got 70% on 200 epochs. And this is the confusion matrix for the 10 classes. You know what would be a good exercise, just to translate everything in JAX. And I like their code because they spelled out every layer, even in attention. They didn't use torch layers. They just used the matrix multiplication. They spelled it out. So I think it would be a good exercise just to find the equivalent layers in JAX, and everything else would be the same. So for example, this piece of code won't change. This one won't change. Yeah. Let me know in the comments if you're interested in JAX translation of Swin Transformer. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, you can find links to the notebooks I'm working on in the description below. Thanks for watching. Bye.